Okay, it's going.
Awesome. Thank you so much. Welcome, everyone. Welcome to today's seminar. This is our first for the semester series of WSU PNL Advanced Grid Institute seminar series. Today, we have with us Alison Colotelo from Pacific Northwest National Lab. She leads hydropower program at PNL. Alison, she serves as the PNL hydropower program lead, supporting multidisciplinary teams engaged in endeavors for the DOE Water Power Technologies Office and the U.S. Army Corps of Engineers. Her professional experience includes over 14 years of basic and applied research on the effects of human development on the environment, as well as project management. She's energized by making connections, solving problems, fostering collaboration, and learning from her colleagues. In addition to Alison's technical work, she enjoys sharing her passion for science with the community through visits to local schools and participation in other scientific outreach activities. Alison will be speaking with us today on investigating the role of hydropower and the electric grid. Welcome, Alison, to the series. We look forward to your speak. Back to your talk. Back to you.
Awesome. Thank you so much. Thank you, everybody, for having me. I really love to do these kinds of presentations, and I hope that you walk away from today learning something new and maybe something that intrigues you. I know your usual format is to save questions for the end. Happy to do that, but feel free to jump in. As I'm speaking, I'll also take some pauses to check for questions. I'll also ask you some questions because you guys aren't getting off scot-free. So just as a warning, there will be some quizzes throughout. But yeah, thank you for taking your time to join, and I really appreciate the invitation. Because a lot of you are students, I wanted to kind of just start a little bit with my background and my journey. Believe it or not, this little kid in the ball pit did not dream of becoming the hydropower program lead at PNNL. I came from a very pro-STEM family, but my parents were not involved in STEM. And so I didn't have any direct examples in my early life to see what it would be like to do research, to study things, or even to get an advanced degree. And it was really a series of opportunities throughout my life that led me to where I am today in the position that I hold. So I was in high school. I got the opportunity to participate in a summer science camp. This is me on an archaeology dig on the Winnipeg River in Manitoba, Canada. This was my first forte into fieldwork, and I learned that I really liked to be outside. I really liked to connect with nature. And it was also my first exposure to grad students, to grad school, to all of those pieces that had been mysteries to me up until that point. And that experience led me to my undergraduate degree in forensic science. Way back when I was in high school, CSI was very popular, and everybody wanted to be on CSI, to be like CSI, and I followed in that path. And I did my undergraduate degree kind of understanding how we can take science and what we know about basic science and apply that to the real world, to solving problems, in this case, understanding how different things came to be in crime scene environments. But during my undergraduate experience, what I learned is that forensic science wasn't going to be the field for me. I didn't feel super invited by the community to be part of that, but I still liked that drive to the outside, and so I had the opportunity to one step back to do my master's looking at the impacts of acidification on lakes in Ontario, Canada. So this is me doing some field work, collecting fish using a gill net, and we were trying to understand how those systems were recovering over time, since acidification had really wiped out a lot of the fish populations. When I finished up my master's, I met somebody from PNNL at a conference, and they had an opportunity that I applied to and was chosen for. And I came out here in 2010 to Richland, where I started as a postmaster's research associate. Postmasters are a really cool term position. So up to 2 years, you get to participate in research that's being done at the National Lab. It's paid. And you get to gain a lot of valuable experience to either help support a career at PNNL or elsewhere. And then over my time, I've kind of navigated into project portfolio management. I'm really organized. I like to make connections, as it said in my bio. And so that led me to my current role now as the hydropower program lead, where I'm helping to support a lot of different teams who are thinking about different aspects of hydropower. And then how do we connect those together so that we can make the difference for the real users of the tools, the information, the data that we're producing at the lab. So how many people have participated in one of these seminars already? Or is this your first one? It's the first one of the semester, but any hands raised? This is the interactive part. You guys gotta know? All right, so PNNL, if you're not familiar, we're one of 17 national labs. We're the one here in the Pacific Northwest, and we're addressing a lot of complex challenges to provide solutions to national needs. Each of the national labs has their own unique capabilities that we're really well known for. PNNL is really well known for our basic science and chemistry, earth sciences and data analytics, as well as our applied work and kind of the energy infrastructure piece, which you can see in the green on the left-hand side of this circle, as well as our national security work, nuclear non-proliferation, and cybersecurity in the red on the right-hand side. And so most of the work that I do is in that green bin, connecting to some of those basic science questions that we have, and basic science process understandings that we do in the blue in the middle. So at PNNL, my role is to support our diverse research teams. We're looking at hydropower systems and ways that we can improve the efficiency of those systems, mitigate the operational risks, and reduce the impact that we have on the Earth systems. And like I said earlier, I have a passion for sharing my science. And so I do a lot of outreach in the community to talk about the research that PNNL does and why it matters to all of us. In my free time, I have two little kids, a 6-year-old and a 4-year-old that keep me super busy. We also have 2 dogs in our family now, so you may hear them in the background in a little bit. So I want to preface this by saying that I am not the thought leader in all of the work that I'm going to present today. I get to represent a number of really smart and crazy talented people that work on the teams that I support. I've listed some of the key PIs here, but this is not an exhaustive list. There's a number of talented folks. In the hydropower program, we have about 250 individuals who contribute to 2 different hydropower studies. And today I'm going to really focus and pinpoint on our work as how hydropower connects to the grid, which is even a smaller subset of that. But just know that I'm just one voice who's representing a ton of work that's being done and a lot of other people who are thinking about these challenges and thinking about what are the technological and science solutions that we need to solve them. Most of the work, all of the work that I'm going to talk about today has been being funded by the Department of Energy. We have funding from mostly the Water Power Technologies Office, but we also get some funding from the Office of Electricity, as well as the Office of Science, particularly their multi-sector dynamics team. So, interactive part. So if you're online, you're welcome to type in the chat. You're welcome to raise your hand, unmute yourself. If you're in the room, you're welcome to raise your hand. Where does our energy come from? If I asked you what is our generation sources in the United States, where would we be getting most of our electricity? Anybody have any thoughts?
I'm going
Carrie.
to go and unmute our students. Hold on a second. Let me do that.
Fossil fuels, hydro, great. Carrie, I was going to pick on you. I know Carrie from our work, natural gas. So in the United States, oh, there we got all of them. That's right. Those are good. In the United States, currently, we're very fossil fuel dominated. So about 60% of our energy is coming from fossil fuels. We've got a little bit from nuclear, and then just about 30%, I think, is from renewables. But if you've paid attention to the current administration priorities, there is a lot of work towards decarbonization. And that means just getting away from those fossil fuels and using more natural, renewable source, renewable resources. And I think, are all of you in the room in Washington State? Yeah, okay. So for those of us, most of us are in Washington. I'm in Richland. I know there could be folks in other places. Here in Washington, we have a lot more renewables on the grid, partly because of the hydropower that we have available. About over 40% of the hydropower in the nation is available in the Pacific Northwest of the United States because of the large rivers that we have, the topography and all of those factors. In Washington State, about 65% of our electricity comes from hydropower alone, but you know that we are getting a lot more wind farms and solar farms coming online every day. We also, as a state, have very ambitious goals around decarbonization and leaning on more renewable fuels moving forward. So as we're moving into this energy transition, this becomes a really important question of what is the role of our current energy sources and how are those going to change as we move into the future? Oh, there you can see kind of the split between some of our renewables. So I'm going to laser focus in on hydropower because that's what I think about 100% of the time. And just to kind of give us some background, what is hydropower? It's really just the power that's harnessed from falling or fast-moving water. And in reality, we've been using energy from these fast-moving water for centuries. Things like sawmills, textile mills, grist mills have been leveraging the energy that's generated there for different services. But it wasn't until the late 19th century that we've really leaned on hydropower to become a source of electricity, the way that I think most of us in the room would think about hydropower today is thinking about that electricity component. But outside of electricity, hydropower provides a number of different services. And so this is another interactive part of the presentation. What are some services that hydropower provides to us as people in the United States? I'll pause. Type it in the chat.
Hello?
Thank you, Carrie.
I don't think we're connected.
I can hear you in the room if you have some thoughts.
Okay. Someone said irrigation in the room.
Okay. Yep, absolutely. Water management, in the chat, Black Start, transportation, flood control, recreation. All right, you guys you know your stuff about hydro. That's great. So yeah, hydropower does provide a lot of electricity to be able to keep our lights on, to be able to make sure my internet's working so that I can talk with you all today. I'm going to talk about this more in depth, but hydropower is also a really important part of our grid stability. So making sure that that we're provided with the electricity that we need when we need it, particularly when we think about how things may change in the future with more renewables, more variable renewables online that are maybe less reliable because the wind needs to be blowing for wind power to work, the sun needs to be shining for solar power. And then others have already pointed these out: transportation, flood control, irrigation support, recreation, all really important services that hydropower provides and that many of us take benefit from. A fun fact is that many of or actually all of the Lower Snake and Columbia River dams, their development was not primarily for electricity. A lot of the development that was done by the Army Corps of Engineers was done to meet some of these other services first, and the generation of power and electricity was actually a secondary or tertiary benefit. And so that's an important part of the conversation when we're thinking about what is the value of hydropower now and in the future. So despite the services, or in addition to the services, there's a number of challenges for hydropower. The number one challenge for hydropower is environmental impact mitigation. I'm a fish biologist by training, and so this is where I started in my hydropower career and exploration. One of the questions that I like to ask is, how many fish do you think successfully pass through hydropower facilities? You all are a lot of power systems engineers. Does anybody have any guess from 0 to 100%? How many fish survive that experience?
Oh, maybe 30%. I don't know.
0, 30?
30% maybe.
Yeah. So actually, the studies that PNNL has done in Clifford he has more insight. The studies that PNNL has done for the Lower Snake and Columbia River dams has showed that more than 90% of fish pass when they're moving from upstream to downstream. So as salmon are going out to the ocean. And so we can, if we think about it really carefully, we can design and operate hydropower facilities to have less of an impact on the environment and still be able to provide the services that we need and we rely on hydropower for. I'll talk a little bit more about some of those investigations later, but just take that away, that the passage and survival can be quite high depending on the design and operation of facilities. Another big challenge for the hydropower community right now, and I think that's probably most pertinent to this group, is revenue stream limits. So valuation, the value of hydropower, has been an increasingly important topic within the hydropower community over the last decade or so. And so a lot of the work that my team has been doing in the hydro grid space has been looking at what are the services hydropower provides, what's that value, and then how do we translate that to monetary compensation. We're also looking at things like climate change and how the changing environment is going to impact the way that we operate facilities. Will we have the water that we need to be able to generate electricity from hydropower facilities in the future with more frequent and severe extreme events? How will that impact the grid, and will we need hydropower to be able to support any of those events? I'm also thinking about modernization. A lot of hydropower is very old, and so we're thinking about digitalizing systems and thinking about updating aging materials and other components within the facilities. So most of the work in our hydro grid portfolio is led out of the HydroWires initiative, which is a research initiative from the Water Power Technologies Office at the Department of Energy. And the goal of this program is to understand, enable, and improve hydropower's contributions to reliability, resilience, and integration within the electricity system. This initiative began probably about 5 years ago at the Department of Energy and is one of the largest programs within the Water Power Technologies Office currently because of the importance to the community as well, or the community from the industry perspective, but as well as to us as energy consumers. So this is kind of a map of the hydropower community, and I think this is important before I dig too far into the research of understanding all of the players that are weighing in, because one of the things that I feel very strongly about is that we can study different parts of the hydropower system and we need to from an efficiency perspective, but we do have to think about how that work translates to the other systems that are connected. If we change operations to meet grid conditions, what does that mean for our environmental impacts? What does that mean for the equipment? And thinking about how all of these pieces are interrelated. So we can do our power systems engineering research in a silo, but those outputs, we need to be able to think about how that translates to the equipment and the infrastructure that we're operating moving forward. So all of these things are connected, and it's our job, I think, as researchers to make sure that we're showing those connections in the best way that we can. When I think about the hydropower community, I have our project partners. Those folks are in blue. They're responsible for hydropower generation, hydroelectric generation. These are plant owners, technology developers, system operators, electric utilities that are generating the electrons and sending them to the customers. We also have our influencers, those that are really affected and want to guide the way that we're thinking about operating hydropower facilities. This is where we have a lot of our river flow stakeholders. So environmental NGOs like American Rivers, tribal entities who are really connected to the waterways and the animals within those waterways. Our resource managers like NOAA, the National Marine Fisheries Service. So we want to see those connections and think about how those folks can uptake the information that we're providing. And then finally, our consumers, that's you and I, but also corporations who are looking at where are their electrons coming from, and in some cases choosing to want to go towards more renewable sources. So what I'm going to share with you today is about the ongoing research and development that PNNL is doing to support hydropower's contribution to the grid, both now as well as in the future. And this is kind of just a layout of the different parts of our portfolio. We have about 16 ongoing projects, 11 different lead investigators on those projects, and they're tackling a lot of different areas. So as I mentioned, kind of hydropower is a series of systems, and even within the hydro and grid portfolio, we have a lot of different research areas that we're pursuing because there's a lot of different science questions that we need to ask. So the first kind of area that I want to talk about is resilience. And how do we think about resilience from a power grid perspective? So there's a lot of things that we know are true. One, we know that the power system is changing rapidly. I think many of you are probably familiar with that from the learnings that you're doing through the Institute. We're also seeing as the grid changes that we're having a lot of rapidly changing weather patterns. And as I mentioned earlier, we see a lot of uptick in the severity and the frequency of extreme events, things like droughts, wildfires, and other heat waves, other types of natural disasters. And those two changing pieces are going to come to a head as we move into the future. So wanting to make sure that we have the reliable energy sources that we need to be able to keep our lights on while also combating some of these increased frequency of weather-related events. So on the right here or the left here, you can see kind of the goals around decarbonization or goals for renewable power by the state. And we have some really aggressive timelines as a nation, but also as states. And so pushing towards more renewable sources is going to really change the grid. And coupling that with the weather patterns, we need to understand how do we make sure that we can keep the lights on. And one of the important pieces that we're thinking about is hydropower's role in that. This chart here shows an example from a heat wave in 2020. So you can see the different colors represent different energy sources that were fitting into the BPA demand resource profile. And so when this heat wave occurred in August of 2020, you can see that the green is the wind completely died down. It almost went to zero. And because of that, California was in severe need of electricity to be able to run air conditioners and things like that because of the heat wave that was associated with that. And what we saw anecdotally was that there was this increase in hydro, the blue bubbles here, that ramped up to be able to provide that electricity so that it could be exported to California to meet their energy demand needs. And this is continuing to occur. There's other instances that we've seen in the last few years where hydropower continues to be relied upon to be able to meet these needs when other renewable power sources are not available. But while there was a lot of anecdotal information within the hydropower community that this was a challenge and that hydropower was providing these services, we didn't have a tool chain or modeling capabilities to be able to understand and quantify what that role really was. And so it was a multinational lab team led by PNNL and embarked on a study to be able to quantify the role of hydropower under these extreme event scenarios to understand what really was hydropower providing and trying to help to put some numbers behind some of these intuitions that the community was having. And so from this work, we were able to quantify historically that hydropower, while it provides about 25% of the installed capacity of generation in the Western interconnection, so the western part of the United States, hydropower in the Pacific Northwest contributed up to 60% of the primary frequency response, keeping the grid stable. Is everybody familiar with primary frequency response? Okay, you guys are power systems engineers. You're like, I got this. All right, so in terms of bang for your buck, hydropower is pulling above its weight in terms of contributions from that primary frequency response. And this is particularly true when we have generation outages that could be because of natural disasters, a climate event, and like I said earlier, as this goes into the future, we may see this continue in terms of the frequency and the duration. So it was really important that we had these modeling tool chains that we were able to quantify that. And then we also ran some simulation studies to be able to look at new scenarios in the future to understand would this be consistent moving forward. And the simulation studies, looking at several different scenarios, were able to show that, again, hydropower is still providing a large amount of that frequency response and also a large contributor of reactive power or voltage support to the grid. And putting those numbers behind, you can see some of the examples here. And so this work really helped to create that framework, and it was the first time that anybody had put together these quantification efforts to be able to put numbers behind that. And this work has been leveraged by the hydropower community, the hydropower industry, to demonstrate this is the services that we're providing, as well as Congress. They've used these types of this information from these studies to be able to help to guide future policy and demonstrate what the value of hydropower could be now and in the future. And this project is continuing. So in the first study, we were looking at kind of individual events from different climate events, but we're also now working on coincidental extreme events. So looking at a heat wave and a drought at the same time and what our hydropower's contribution. I'll share these slides, but the final report is linked in this slide as well if you're interested in reading more of the science piece of it. So before I move on to kind of water systems, any questions, thoughts, observations about kind of hydropower's contribution to grid resilience?
Quick question, maybe Alison, from me. So the study is really impressive. My question is, did you look into the future projection for the climate change and how it will affect the hydropower generation and what will be the impact in terms of grid resiliency?
Yeah, so that's this follow-up study is going to be looking more into the future. So in the original study, we were looking at the 2018 planning case from the WEC, I believe.
Okay.
And then this new study that they're doing, I believe they're using the 2030 planning case for the WEC. So looking at the new generation profiles, as well as trying to get a handle on, I mean, they're climate projections, so they're not going to be perfect, but trying to leverage the best available climate science to inform what's likely to occur and then how might hydropower respond.
Awesome. Thank you.
Any other questions? Thoughts? Clear as mud. Awesome. So the next kind of theme that I want to talk about is water and how do we translate the available water, which water is the fuel for hydropower. How do we translate that to power system studies and a lot of the work that all of you are doing? And I show this figure because I think it highlights some of my earlier comments about the systems. the water systems, and if we could just think about the hydrology and water availability, the power systems, the facilities, we could all look at these in separate, but we need to understand, to really show the application of this work, how these connect together, and how these pieces of how these systems fit together. So I just want to just at a high level, hydropower representation in the bulk system models, and you all know more about this than I do. There's a few different ways that it can be represented. What I'm going to focus on today is really about reliability studies. That was the focus of the research that we're doing. But just knowing that there are different ways to represent depending on the questions, and we're just going to really focus on those reliability studies for right now. Oh. Sorry, can you all see all the whole title? Or is my little black bar in the way?
We can see the whole title.
Oh, okay. All right. It's just me. Good. All right. So when we started this project, I should lead in with this work was driven by an industry workshop that PNNL and NREL hosted in 2019 with the hydropower community, trying to understand what are the biggest problems that we need to tackle. And one of the key findings from that was we need to have better representation of hydropower within power systems models. In some cases, in some of the dynamic stability models that the WEC is using, up until recently, those models were 30, 40 years old, and so not really representative of what we know about the hydrology and water availability today. And so that workshop really led us into how do we better represent hydropower so that we don't have errors, these feasibility errors, in terms of what we're thinking hydropower can provide for scheduling purposes. So at the time, and I think a lot of the status quo right now is that we're doing monthly representation of water availability in power systems models. But if any of you have ever gone out and looked at a river, it changes much more dynamically than that. And so we wanted to get to more fine scale representation of water. Weekly was the target to be able to make sure that we were able to accurately clarify what water was available, what hydrogeneration could be at an easier time step. If we're only relying on the monthly, it's very ill-refined, and you see a lot more errors that you can see here. And so our team, this is led by Natalie Voisin, is our lead scientist here. They developed some weekly hydropower data sets for the bulk systems models. They looked across the West, across the Western interconnection, looking at over 300 hydropower facilities to be able to compile all of this information and provide these weekly data sets. They looked at different water conditions, so dry years, wet years, and kind of an average year, and created these data sets in a way that they could be integrated into production cost models or for other research purposes, so that hydropower schedulers could take that information and better inform their own planning. And what we found through the development of these data sets is that by transitioning to these weekly data sets, that we were able to provide a lot more insight into the grid resilience that hydropower is providing. So a lot less of a difference in terms of what was projected versus what actually happened, which leads to less overconfidence and just more realistic conditions, better planning, more efficiencies from that perspective. And so these data sets have been integrated into a lot of the highly used production cost models. Many of you may be familiar with Plexos as well as GridView. And so we're integrated into both of those. We've also been working with the WEC to use our hydropower data sets to inform their 2032 planning case. And we're leveraging these data sets for a number of other efforts that are funded by Office of Science as well as the Office of Electricity. So as you all are doing your research and learning about these systems, you may have the opportunity to stumble upon the data sets that were created by PNNL. Any questions about the water representation? Don't ask me any hard questions, please.
Can you hear me?
Yeah.
Yeah, I'm just wondering, how do you make those data sets? Like, where do you get the data from? And what
Ooh.
is that cost model looks like?
That's a good
Well,
question.
if I have to do it, like if I have to do it for some other region, how would I go about it?
That is, I will admit, is outside of my skill set.
Okay.
But I can connect you with the people who know how to do that. So they are working on the publications to be able to represent this. Yeah, but yeah, I'm not going to pretend to try to fumble through that one. I'm sorry.
No worries. Thank you.
Any other questions? Please make them a little easier. Or ask me a fish question. I got no fish questions.
I guess on that focus, around here, if you ever hear someone speak against hydropower, it's pretty much 100% of the time it's referring to salmon populations decreasing, and they're attributing that to hydropower. As someone with a background in that, could you speak to whether that's an accurate representation of what's causing the decline, or what's a more accurate way to attribute what's going on?
That's a loaded question. It's a really good question, right? I've been harping on these systems and how things are connected together. And I'm going to share in this example here that I present next, I'm going to share some of the recent research that PNNL has developed around trying to understand fish passage through hydropower facilities. But honestly, it's very complicated. Hydropower is one of the is a contributor to the decline of salmon in the Pacific Northwest. The altering of habitats, you can see here, blocking, limiting access for fish. If anybody's familiar with Grand Coulee or Chief Joseph Dam, there's currently ongoing efforts, largely driven by the Upper Columbia United Tribes, to reintroduce fish above those dams that haven't been there for 70 years. The construction of Grand Coulee and Chief Joseph dams have blocked about 30% of salmon habitat, going up into Canada, into Idaho and Montana. So it's not that it isn't a factor. I think there are a lot of pieces that we need to think about in terms of how to move forward. Thinking about what are the other pieces that are affecting salmon life cycles? Salmon spend about 3 to 5 years in the ocean. And that's a large black box right now, and trying to understand how that fits into the larger piece of their life cycle. We've done a lot of research, a lot of work to improve fish passage through hydropower facilities. As I mentioned earlier, at a lot of our facilities, we're seeing fish surviving at over 90%. And so I think we need to think about these questions holistically, and also need to think about what are the things that we want to choose. What are the priorities that we have as a society to be able to move forward? As PNNL, I'm here to present the research that we are doing, and that will inform policy, that will inform decision makers. I don't have a position. I want to make sure that we have the best available research and science so that those decision makers can make the best decisions possible. You all as taxpayers, as voters, hopefully you also have a say in that in terms of how things move forward. So let's talk about it a little bit more, because I think you're right. Not just here in the Northwest, but it is very heightened here. Hydropower and the environment are often at odds, right? There's a lot of times it's you have to pick one or the other. Either we have energy or we have protected fish. And a lot of the work that we've been doing recently is trying to understand, is there something that we could do differently, better, so that we don't have to make such drastic choices? So hydropower blocks fish access. I talked about that. Changes the water quality. That's bad for fish. Increased temperatures, slower flows. That tends to be bad for fish. And then changes in habitat. And as I mentioned, a lot of times we're asked with, or we're posed with these questions of where do we choose? Where do we trade off? A lot of the future of the grid is looking at ancillary service markets, requiring flexibility so that we can be able to respond to when the sun isn't shining or the wind isn't blowing, or we have these larger outages on the grid, and we're asking hydropower to ramp up or down. Those dramatic changes in operations also can lead to dramatic changes in the water levels downstream. That can affect fish, wildlife, recreation. So a lot of potential negative impacts that we're thinking about. And one of the studies that PNNL is now leading is looking at these trade-offs between grid and the environment. And before this, nobody had ever really looked at these two systems together. We've always kind of looked at it in silos. And so our team put together, they looked at a bunch of different grid services that hydropower provides, and then they looked at the flows that are prescribed by FERC licenses. And so these are basically just the regulatory requirements that are set by different regulatory agencies, mainly FERC, but there are others that say you might need a minimum or prescribed or different flows. But you can see the connection between where those grid services impact those flows available. So the red means that there's not a lot of overlap in terms of you can have both. So spinning reserves and or non-spinning reserves and prescribed flow. Voltage voltage support, you can see a little bit more of that, the green, so that's highlighting where there's less of an impact on the environment from those particular grid services. Does that make sense? I know that's a little complex, but. So that was the first step, just to kind of think about, okay, how are these things connected? We have some really fancy spider web charts that, but it's been summarized into this table. And PNNL and other national labs are now developing a tool that can be used by different stakeholders within the hydropower community. This could be the dam operators or river flow stakeholders that could use to be able to look at what are the energy and environment outcomes when we look at different flow regimes in the future. So the user would be able to put in what their proposed flows might be, or we could create some optimized flows of this is the way that water would be discharged through the hydropower facility. We take that information and quantify different fish habitat and connectivity metrics based on those flows. So telling us, are these good for the fish that are in that specific basin, or are these ideal situations? And then we can translate that information to looking at where are those trade-offs happening? Where do we need to make those decisions so that, again, stakeholders and these decision makers have the information available about, okay, if we choose this from a habitat perspective, what does that mean from a generation or an electricity perspective? And so it's not deciding that for them, but it's helping to provide that information that hasn't been available before. We haven't been able to compare these side by side. And if you're interested in more, there's a report out that goes into this a lot more in detail, but this being one of the very first places where we're able to kind of look at those two systems, the environment and the grid kind of overlapping and looking to see how do these things interact with each other in the real world. And then finally, I just wanted to present a case study. This is a paper that was recently published in the Canadian Journal of Fisheries and Aquatic Sciences. As power systems engineers, I bet you don't pick up that journal very often. But this was a project that was funded by BPA. They wanted to understand what are the factors that affect powerhouse passage of salmon or smolts. That's a lot of jargon, I recognize. So the powerhouse, right, is the part of the dam that's making electricity. Smolts are salmon who are heading from freshwater to the ocean. So what is causing fish to go more through the powerhouse versus the spillway or other routes at the dam? And for context, powerhouse passage tends to be the lowest survival. We tend to want to guide fish away from the powerhouse. And so that's where they were trying to understand what are the factors that are really affecting fish and forcing them or encouraging them to go through the powerhouse. And could we do anything from an operational perspective to change that? PNNL is really well known for our acoustic telemetry sensor systems. We've been doing those studies for decades now in the Lower Snake and Columbia Rivers, collecting a lot of data about how fish behave around hydropower facilities under different operating conditions. And so we were able to do a retroactive a study with the data, looking backwards to see what are those factors that were available, and how does that translate to fish survival if we change those situations. What we were able to see is that, so if we're diverting water away from the powerhouse, that means that there's less water availability for generation, less available for electricity. And so again, that trade-off, that do we have to choose one or the other? And so what we were able to see with this study is that there are operational conditions that may be able to have better survival for fish, but also to provide opportunities for generation to meet some of the grid services that we're asking hydropower to provide here in the Northwest. So some hope, some new research that's able to see that we might be able to look at things differently than we have in the past with more sophisticated science and technology to be able to answer some of these really complex challenges. So that's what I have for you today. I hope that this was informative, useful, a good use of your time. I'm happy to take any questions or have any further discussion with you all, but thanks again for joining.
Thank you, Alison, for a really interesting presentation and sharing all the research in this space that's going on at PNNL. We're open for questions. If you're online, please either post your question or raise your hand and I'll call you. And students, please, feel free to unmute yourself and ask questions. Okay, we have an online. Alan, please go ahead. Alan, I think you're muted. We still can't hear you. Okay. While Alan is trying to connect, any other questions? Yeah. Oh, no, that's fine. Yeah, go ahead.
Alison, I appreciate your take very much. It's quite interesting. I've got a field of questions. A related technology of tidal power generation. Tidal power is fully predictable. Your wind example, where there was no wind for a vast period of time, it's close to large population centers along the coasts, both in the east and in the west. And my question is there any work going on in that area? Obviously, it shares some of the similar kinds of concerns about environmental degradation, species, and so on. But the reserves of power must be just immense from tidal power, tidal changes, particularly in the Northwest, but also in the Northeast, where you get 12, 14 foot time change in confined space. So I don't know. I just wanted to get your thought about that, and if there's any work going on in PNNL or other places that you're aware of.
Yeah, great question. I will preface it that I'm not a tidal or a marine energy expert, but the Water Power Technologies office that I do a lot of my work for, they have a hydropower part and a marine energy. So definitely are things that are going on in there. And PNNL is well positioned and doing a lot of research. A lot of our strength is in the environmental performance of tidal or other wave energy devices. And at this point, marine energy is theoretical in the United States. We've got maybe a few little examples, right? But my understanding is that Europe is definitely the leader in terms of actually deploying these things. And so there's a couple good things about that. One is, to your point about the environmental protections, we've been able to learn a lot about how we generate electricity from water, and how to reduce the environmental impacts. And so PNNL has a large portfolio of projects that's looking at, okay, when marine energy is deployed and is supporting the US's generation mix, are we designing these facilities in a way, or these structures in a way, that they're going to have less impact on the environment? And all the evidence points to yes. They're designing them at slower speeds, putting them in places away from migratory pathways. Obviously, there's never going to be no impact, but there is a lot of thought and care going into making sure that we're designing these things better in the future. So that's a good thing. We haven't really been able to, we're just scratching the surface in terms of how marine energy is going to support the grid. And you're right in that there are a lot of opportunities kind of near and close to the coast. One of the pieces that I think is really important is working with the communities that are on those coastal areas to make sure that marine energy devices are suiting their needs, and that we're working with those communities where we're deploying. It's not just going to go in and deploy those, but making sure that we're working with the communities to address their needs and concerns as we think about that development. So I know PNNL does have a project that's looking at kind of the value of marine energy to the grid, but that's where we are right now. We really haven't gotten started as deep as we have in hydropower in terms of what are those specific contributions and how do we interconnect. I know in the offshore wind space, just connecting offshore wind to the grid is still a huge conversation, right? And so we're a lot. We're still learning a lot in the marine space, but that means that we can hopefully do it better than we have with other technologies, right?
Great, thank you.
Other questions? Yeah, go ahead, unmute yourself. Yeah.
Okay, so my question is a bit connected to what to the last question. So it's about the connection between the environmental impact, the social impact, and the Indian tribes that we have, especially in Washington State, for example. So is there any positive or negative impact between having to take on a lot of hydro projects or even the existing ones? I mean, what's the relationship between these, and how does the Indian tribes view, the presence of hydro systems, and also in terms of the survival of fish, because it seems there's a bit of connection, right?
Mm-hmm. Yeah, I won't pretend to, or I won't speak for Indigenous people and their perspectives. I think it varies. There's a lot of diversity in terms of what people think and what their priorities are. I think the important piece is, like I said earlier, we need to connect with the communities that are in the spaces where these energy systems are to be able to understand what the best path forward is. And I don't think there's going to be a one size fits all approach. I think the one size fits all is how we engage with the community and how we're responsive to their needs. And so that's really where a lot of the work that we've been doing so far has been focusing, is how do we engage appropriately with the communities that will be impacted by these developments and these operations.
All right, thank you.
I will say on the hydropower side, the Upper Columbia United Tribes I mentioned earlier, they have a lot of efforts right now around reintroducing fish above Grand Coulee and Chief Joseph. They're just releasing this week. They just released the first of 3 videos that's focusing on their efforts for reintroduction. I can find the link and drop it in the chat. I would recommend everybody watch it. Just as a human, I think it's a really amazing story of what they're doing to bring back fish to their area. And one of the things that one of the people in the video states is they recognize the benefits of hydropower, and they also want to move forward and try to understand how they can have fish, anadromous fish, salmon, back into their areas. And so I think it's something for all of us, especially us that are in the research space, is understanding how our research does impact different communities. And so it's a really good series. Made me cry the first time I watched the whole thing, but I'll put the link in the chat if anybody's interested, because I think it's good to see all of those different perspectives.
Yep. Thank you. Any other questions? If not, I had a question, Alison, and this is again going back to the study that PNNL did on how hydropower is supporting the resiliency of the grid and moving forward what we're looking into. So my question is more from the perspective of we are integrating a lot of renewables and we know that we require storage resources to really make them viable, right? Has there been any studies in terms of, trade-off and cost benefit from hydro or pump storage solutions and installing new of those from a storage perspective, not just the generation perspective? And what does it look like, looking at the climate change projections and looking at how much, Pacific Northwest is reliant on hydropower? Is there some good study that you can point to on those things?
Yeah, I mean, I think that's a huge part of the conversation, right? Part of that flexibility is that ability to store water, and that varies depending on your hydropower facility. Currently, pump storage hydropower provides about 90% of our long duration storage in the United States. And so it is looked at as an important resource as we're thinking about how do we store, how do we make sure that we can have a reliable and resilient grid. I didn't dig into that during this presentation, but it's definitely a topic of interest. I'm trying to think of, there's a few different studies and papers that I could definitely drop in the chat that are kind of talking about what that role looks like.
Okay, awesome. Thank you. So we are close to 3 p.m. Actually, we are at 3 p.m. Thank you again, Alison, for the wonderful presentation, and thank you everyone for attending the talk. And let's thank our speaker once again for spending time with her. And please feel free to follow up with her if you have any follow-up questions, and if you want to learn anything more. With that, we'll conclude today's seminar. And thanks again, everyone, for attending, and have a wonderful day. I don't know.
Thank you.
That's great. Thanks for unmuting, students. Awesome. Thanks, everyone. Have a wonderful day. Thanks, Alison. Bye.
Thank you.
Thanks.